So, hello everyone. We are Team Cranspace from Cranfield University in the United Kingdom. We're currently astronautics and space engineering students. So to give you a quick overview of our presentation, we'll give you the mission outline, which you've heard many times already. We'll introduce our solution to you. That will be going over our trajectory, and then we'll introduce relevant subsystems along the way to our journey to Mars, starting at launch and ending at reentry. We'll finally end on mission costs and a summary. So our mission statement is to send 2 people on a flyby of Mars to be launched by the end of 2024, and to recapture the imagination of the American public and give direction back to the space program. So we approach this project through the systems engineering approach, taking the mission drivers, creating the requirements, producing the trade-offs, and eventually coming up with our Cranspace solution. So looking at some of the drivers, we're sending the largest payload mass to Mars. This requires a significant amount of propulsion, and getting all of this into low Earth orbit is an initial challenge. We'll be setting new records for our astronauts, being the furthest distance from Earth, as well as the longest consecutive duration in space. The effects of space travel are well known from the ISS, so tackling these is a core issue. Solar radiation, as you've heard, we will be launching near the solar maximum peak of 2024, and as NASA has tight requirements on dosage for their astronauts, this was a key challenge. No resupply missions are available, so bringing all the consumables is necessary, and reducing the mass of consumables to a tolerable level is also very important. And finally, failure away from Earth is potentially disastrous, as there's no easy way home. So taking our drivers, we came up with our top-level system requirements. These were essential in the successful design of our spacecraft, and they cover areas including crew safety, technology, and scheduling. To complement our requirements, we have the design and risk philosophy. This was technology heritage, the backbone of the Cranspace design for the cost-effective, quick, and low-risk mission. So we reduce implementation risk, less time spent on research and development, less uncertainty in margins as we will not be using novel technology. We also reduce mission risk as we can draw on lessons learned, as well as targeted mitigation techniques for known issues of the systems that we'll be using. Emphasis is also placed on redundancy to reduce critical single-point failures within the design, especially the life support. So this is the Cranspace solution, TOTEM, the transfer vehicle for observation, testing, and exploration of Mars. Going through the spacecraft, we can see it is made up of 3 key elements: a crew capsule for Earth ascent and descent, a habitat module for living, and a propulsion system to provide the trans-Mars injection. So each component was selected through the systems method, driving requirements, trade-offs, and the solution. We compared many different types of spacecraft, the Orion, the Starliner, and the Dragon. However, we felt, and the trade-offs confirmed, that the Orion was the best option, as it reduced the design uncertainty as it's further in its development program. We also felt that window size was very important for the astronauts during the flyby, and as the Orion had larger windows. The Orion will also be internally augmented to help adapt it to a crew of 2. The habitat module was necessary because the Orion didn't contain the NASA standard requirements for long duration volume of 5.1 meters cubed per astronaut. So to accommodate this, we needed an additional habitat. So a lot of people have used inflatables and said inflatables will or can be the future for Mars travel, but not for this mission, as we are doing this, going through the heritage approach, reducing cost. The multi-purpose logistics module was the best option for various reasons, including that it's been built 5 times, and there's heritage in the modification of it, as one has been modified to be a permanent module on the International Space Station, where it's been for 5 years. To modify the MPLM, we'll be adding an internal radiation protection And it will also benefit from additional non-pressurized volume through the use of a service module taking heritage from Cygnus. The propulsion system was chosen as the exploration upper stage. A single launch to orbit means it reduces complexity, increases safety, and reduces cost, as we considered multiple launches of smaller spacecraft upper stages. However, increasing orbital rendezvous and docking increased risk. A custom interface will need to be designed to allow the exploration upper stage to attach to the multipurpose logistics module. So looking at the mass breakdown, we can see that we're sending 147 tons to low Earth orbit with a payload mass of approximately 30%, and 10% of that is margin. So looking at the payload breakdown, including the margin, you can see we have just under 42 tons, which will be reaching Mars. This includes propellant for AOCS, radiation shielding, and you can see the majority of the mass actually comes from the Orion capsule and its service module. I would now like to hand you over to Rob, who will go through the trajectory.
Thank you very much, Will. Now, the first subsystem level design decision that really has to be made is the trajectory, as this drives many aspects of both the spacecraft design and the mission schedule. Our baseline trajectory was the very popular 2021 Mars-Venus flyby opportunity. This was traded off against a number of direct Mars flyby trajectories, which were generated by optimizing a Pachaconic-based approximation of the trajectory. You can see one such candidate here on the right. Trading off these candidates in terms of the mission duration and delta V requirements and Earth return velocity, as well as how close they were to the 2024 solar maximum, led us to decide that our baseline trajectory was in fact the ideal one for this mission. Not only does this give us 2 flybys for the price of 1, but it is also a free return trajectory requiring only 1 major burn from the spacecraft. It has a reasonable duration and delta V to depart low Earth orbit. And in terms of the schedule resulting from this, the main events are, of course, the launch and assembly of the spacecraft in November 2021. This will be followed by a Venus flyby in April 2022, a Mars flyby in October of that year, and a return to Earth in late June 2023, at which point the astronauts will have traveled over 250 million kilometers through interplanetary space. I'd now like to start going into a bit more depth in this mission outline and touching on some of the relevant subsystem design decisions along the way. The first event, of course, is launch. As has previously been mentioned, the amount of payload we need to send to this trajectory with a C3 of approximately 20 is significantly higher than the single launch capability of any existing or, as far as we know, in development launch vehicle. A number of multiple launch architectures were therefore compared, and in the end, the ideal one for our purposes was a 2-launch strategy using the SLS Block 1B and the Falcon Heavy. The first launch of the Orion capsule with the crew, as well as our MPLM-based habitat module, would take place at least 1 week before our Trans-Mars injection burn window. Not only is Falcon Heavy a human-rated launch vehicle which should have significant flight experience by 2021, but its nominal payload to low Earth orbit of 53 tons gives us significant margin for both our payload and the necessary custom fairing, as well as the Orion's launch escape system. Much closer to the TMI window, the SLS Block 1B would launch. This would carry a very small payload consisting purely of the structural adapter between the exploration upper stage and our habitat module, shown here in a non-standard, shorter than usual payload fairing. This this very small payload to orbit means that enough propellant would remain in the exploration upper stage to carry out our Earth escape burn using only a single stage and a single burn. As well as the fact that, or alongside the fact that SLS Block 1B is expected to be, or should be ready in time, the use of a single stage in this way will reduce mission risk and factors such as propellant boil-off. Now, in the week between these two launches, a number of activities will happen. First of which, of course, is after the Falcon Heavy launch, the Orion capsule and MPLM habitat module will separate from the upper stage and dock in low Earth orbit. This will allow the astronauts to enter the habitat module and perform system checks to ensure that everything is ready for the Earth escape burn. Again, once we're satisfied that everything is go for launch and much closer to the launch window, the SLS will launch, and using the AOCS subsystems of both the spacecraft and the exploration upper stage, the two halves of Totem will rendezvous and dock in low Earth orbit. Based on ISS docking procedures, we estimate that 8 hours should be enough for this, minimizing propellant boil-off in the exploration upper stage. Once the spacecraft is fully assembled and all systems have been checked, the exploration upper stage will reignite, providing the necessary approximately 4.1 kilometers per second of delta V to our spacecraft. At this point, the exploration upper stage will remain attached for thermal reasons, and this really represents a point of no return for the astronauts. In other words, they'll have plenty of time to get familiar with the internal configuration of their spacecraft. The MPLM will be outfitted with up to 24 international standard payload racks to contain all of the necessary equipment and supplies for the astronauts' survival and comfort, and this will still leave them with at least 24 cubic meters of additional free habitable volume. It's likely that the overall layout of the habitat module will be loosely based on that of the Zvezda module, which was a fully self-contained space station module containing everything necessary for astronaut health and comfort, such as separate areas for hygiene, sleeping, and science. Another design issue which will become significant right from the beginning of the mission is the deep space radiation environment. In order to keep the astronauts' predicted radiation dose to acceptable levels, a 5.5 centimeter thick layer of polyethylene will line the habitat module. In addition to this, the astronauts' crew sleeping quarters will have a much thicker layer of polyethylene. This has two benefits. One is that, of course, it reduces their average radiation dose, as it is expected the astronauts to spend about a third of each day in their sleeping compartments. On top of this, it provides fulfills the very important function of providing a storm shelter, which the astronauts can take refuge in the unpredictable event of a solar particle event causing brief increases in radiation. Our first big milestone in the mission will be our Venus flyby approximately 5 months into the mission. I'd now like to hand over to Roland, who will take you on the rest of our journey through the solar system.
Thank you, Rob. So our closest point throughout our Venus flyby will be 11,000 kilometers above the surface, and really going into Venus's neighborhood, as has been pointed out multiple times, really poses a key engineering challenge when it comes to the thermal energy that is affecting the spacecraft. So as you can see here, at Venus we'll be experiencing roughly twice the thermal energy per square meter as we would at Earth, and we have exactly the opposite problem when we're going to Mars. So really thermally balancing a spacecraft is the key challenge here. So for Venus, we are proposing to use the exploration upper stage as a sunshade in order to keep the manned part of the spacecraft hidden, and therefore try and balance out the spacecraft thermally that way. And in terms of Mars, we'll be looking at using standard heaters and a variable circuit throughout the spacecraft in order to account for the additional heat we will need. In terms of solar power generation, this also poses a problem as we have to generate 7.2 kilowatts of power throughout our journey. That is with a 40% margin. And so we've sized our solar panels to work appropriately at Mars. However, that means we'd be generating too much power when we're in the vicinity of Earth or Venus. So we have to angle those solar panels to induce cosine losses and guarantee a steady generation of power. So having completed our flyby, it's time to have a little bit of a look at our consumables. For example, our oxygen generation system. So here we met a really hard requirement of 0.835 kilograms per crew member per day. We can't change that. So really for us, mass efficiency was the key driver here in order to keep down the payload mass overall of the spacecraft. However, this can also lead to issues as, for example, if you play with the pressure a little bit, if we reduce the amount of pressure in the cabin, we wouldn't have to take as much nitrogen as we do currently. However, that would lead to a decrease in performance of the crew members, so we discarded that idea. In terms of our solution, we'll be using the Sabater process, taking CO2 and hydrogen and producing methane and water, and then through electrolysis we can generate oxygen that way. The actual hardware, we're assuming an improved version of the current ISS oxygen generation system, which literature predicts has an efficiency of 75% at the time of launch. So this is what we've assumed. In terms of our other consumables, we're looking at a food mass of 755 kilograms. Again, there's not much we can change about how much people eat. So the only thing we can really do is dehydrate the food in order to save a bit of volume when we're packing. So as you can see, there's a bit of a pattern here. Water really is the key ingredient to completing such a mission successfully. So this is where a lot of emphasis is placed, and we're looking at using a scaled-down version of the ISS water processor assembly, which is not a closed-loop system, but we're looking for appropriate high efficiencies as is currently predicted on the ISS system. So after our Venus flyby, the next port of call is our Mars flyby, which is the closest approach altitude of 350 kilometers. So this is the big moment. This is the reason we went on this journey, and this is a good moment to talk about all our science experiments that we'll be undertaking throughout this journey. So we really see this mission as a test bed for technology for future manned missions. So we propose taking things along such as our high data rate laser communication system and biological life support packages. These will purely be proof of concept and will not affect the integrity of the life support system in any way. And in terms of deep space science, we're looking at recoverable interplanetary tests, things we can mount on the capsule and take back down to Earth, and we'll have enough time and all the instruments in the world to analyze the samples, as well as a study of bacteria survival time. The key issue whenever you launch a spacecraft is sterilization. How long does bacteria last on the outside of a spacecraft? And this is a good opportunity to test that, and when we're bringing back our capsule, we can investigate the results. And for planetary science, we are suggesting the use of surface penetrators. If you're not familiar with them, that's basically an artillery shell filled with instruments. And you can just sort of fire it at Mars. It will impact Mars at 300 meters per second, and that's really a cheap and simple way of doing some additional science. In terms of human science, obviously the psychological and physiological effects of human space travel will have to be studied deeply. And this is really a key issue in general, as we're breaking the record for duration in terms of a manned mission. So we're really looking at combating those already known issues of manned spaceflight, such as regular communication sessions with Earth, with psychologists, with friends and family, circadian lighting cycle in order to mimic conditions on Earth, and using VR headsets to kind of break the monotony of being in the same tin can for 580 days. And in terms of the physical aspect, we're looking at supplements to combat bone density decrease. And as on Earth, the same principle applies. Exercise, exercise, exercise. They need to be fit, they need to be healthy, they need to be strong for the next phase of our mission, which is reentry. So our key reentry event will be the Orion undocking from the MPLM. So there's only one undocking taking place, reducing complexity and risk of anything going wrong. And we'll be using a skip reentry technique with two 50-second periods of above 5G with a peak G loading of 80 G, which is, you can roughly compare that to what an Air Force pilot might experience during testing. So, having landed, we need to have a look at how much money we spend. And we're projecting that will be about $4.7 billion US with a 45% margin. And our peak monthly investment will take place here, which is during construction. That's about $100 million in a month, which is 5% of NASA's monthly budget. So we really think that is doable. And just, you have some figures here to compare that to how much the Apollo missions cost. So how do we get those numbers? We use the cost estimating relationships based on the costs of an Orion module, an MPLM, and an SLS. And then we used RAP factors and the NASA reserve factors to get our margins. And then we compared that overall total number with the Johnson Advanced Mission Cost Model, and we got similar numbers. So that gives us that little bit of extra confidence in our projections. What does that look like in a bit of a breakdown? You can see here our big main factors are the Orion capsule and the interfacing and testing. So these are two areas that have to be monitored quite closely in order to avoid going over budget. So in summary, heritage is the #1 aspect of the Cranspace design solution. We'll be using the Orion, MPLM, and Exploration upper stage, which all will have flight heritage and engineering heritage. We'll only be using 2 launches, therefore reducing risk of the mission failing early on. We have a mission duration of 580 days using the standard Earth, Venus, Mars, Earth trajectory, and a payload for Mars flyby of 42 tons with a habitable volume of 33 cubic meters, which is well above the minimum that NASA sets for a long-term space mission. And we'll be doing all of that for $4.7 billion US. So this really shows that it's possible over the next 8 years to take the next big step towards a manned Mars landing and building momentum and inspiring a future generation to explore another planet, not because it's easy, but because it's necessary. Thank you very much. I'd like to invite the rest of the team up for questions.
Questions? Jürgen? I thought I understood that you intend the total launch mass from Earth is 147 tons. Yeah, and for the second launch, you have indicated 104 tons. If this is so, which launcher can launch 104 tons in one launch?
Thank you. So the 104 tons on the SLS Block 1B slide included both the, it included both the propellant and inert mass of the upper stage. The nominal maximum payload to LEO of SLS Block 1B, last I heard, was 105 tons. But of course, that doesn't include the upper stage inert mass, so it should be obviously, this isn't a standard launch as we as it's not, as the thing of interest is just the upper stage rather than a payload on top of it. Does that
so there's
answer
a
your
part
question?
of mass in which belongs normally to the launcher, or how do you understand that? I mean,
that's correct, yes.
It's a calculation, just a calculation.
Yes, so that's correct. So the
a little bit misleading. Huh?
yeah, it's possibly a bit ambiguous, but
Okay.
so the do we have a backup slide here? With recycling, we should need only about 300 kilograms of water. As the 5 tons mentioned initially would be the mass that would have been required if no recycling took place. However, with the almost closed loop system, we assumed only a few hundred kilograms was necessary. In practice, with some improvements to the ISS, it may be possible to fully close the loop, but you'd probably still want some water along for reserves in case it was necessary.
All right, thank you very much.
Thank you.